Hi. Now, when we are comfortable with the concept of the conditional expectation, we are ready to define martingales. We just need one small definition because when we talk about martingales, they're usually martingales with respect to a filtration. So we need to define a filtration first. So a filtration is simply a sequence of growing sigma algebras. So they all lie within our big sigma algebra sigma, and they're getting bigger. So definition: an increasing sequence of sigma algebras F0, which belongs to F1, which belongs to F2, and so on, and they all also belong to sigma, is called a filtration. When I say belong here, I also allow them to be equal. So it's just that every set which belongs to this sigma algebra must belong to this sigma algebra, and so on for all of them. Okay, so this is a filtration. And second thing which I want to define is I want to say that a sequence of random variables is adapted to a filtration. So xn, and when we talk about martingales, and we will be talking about martingales very soon, we talk about sequences of random variables starting at n equals 0. And then I would call such sequences processes. There is not much difference with the sequences. So a process xn, n greater or equal than 0. So let me make it clear here that nothing major is happening. This is just a random sequence of random variables. Okay, so a process xn is said to be adapted to a filtration fn. If each xn is measurable with respect to the corresponding fn. So if xn is fn measurable, for every n. And there is a very special filtration corresponding to each process, which is called the natural filtration. So which growing sequence of sigma algebras could it be? So let's look at the following. So let's take the sigma algebra generated by the first, indexed 0 random variable. Now let's look at the sigma algebra generated by both sigma 0 and, x0 and x1. Now which one is bigger? The second one is bigger because it contains pre-images under x0 and pre-images under x1, while the first one only contains pre-images under x0. So, then if I add more random variables, then I get this increasing sequence of sigma algebras, x2, and so on. And this filtration is called the natural filtration of the process xn. So is the natural filtration of xn. Why is it good to have the natural filtration, because each process is automatically adapted with respect to its natural filtration. Because which property do we need to check? We need to check that x naught is measurable with respect to its own sigma algebra, sigma x naught, which is by definition the case. We need to check that x1 is measurable with respect to this sigma algebra, which is true because it is generated in particular by x1. But so why do we include it? Why have we included x0 then? Well, to make them increasing, right? So for measurability, for adaptedness, we only need to include the last random variable. But for the sigma algebras to be growing, we need to include all the previous ones. So this is a natural filtration. Let's make this comment that every process is always adapted with respect to its natural filtration. And if in the sequel the filtration is omitted in an example or somewhere, then you can always assume we are talking about the natural filtration. Otherwise, the filtration would be given to you explicitly. But very, very often, it's just enough to consider the natural filtration. Okay, so we defined a filtration. We defined what it means to say to be adapted, and we defined the natural filtration. Now, before we give the definition of a martingale, I want to give you an idea of what it is all about. So martingales are random processes which correspond to fair games. So fair random games, fair betting games, if you like. So let me start with this example here, where my game will consist of 2 rounds. So it goes over 2 days. So I start with 0 amount of money, and then I flip a coin, and depending on the value of the coin with probability 1/2, I either go up, so my capital either goes up or it goes down. And then wherever I am, I flip another coin. And if I am here at day 1, so if my capital at day 1 is 1, then according to what the coin tells me, I either stay at 1, so if the coin shows tails, and I go up to 2 if the coin shows heads. So with probability 1/2, I increase my capital. With probability 1/2, it remains the same. And what happens if I had lost at day 1? Well, again, I flip a coin, but then I can either lose even more. Oops. I can either lose even more and end up with -2, or I can keep the same amount of money. So each outcome happens with probability 1/2, independently of what happened at day 1. So the main question I would like to raise here is this game fair? And in a way, you might think, well, yes, because our expected capital at day 2 is 0, right? And our expected capital at day 1 is 0, and our initial capital is 0, 2. So over those 2 days, I will not win on average on day 1. I will not win on average or lose on day 2. So is it fair? I mean, in a way it's fair, but it's not fair enough, because it is not fair from day to day. So what I really want, I want that if I take any 2 days, and in this example, I want to take this pair of days, 1 and 2, then if I if I was sitting here, then I know I'm going to win from day 1 to day 2. And if I'm sitting here on day 1 with -£1, then I know that I'm going to lose even more on average, right? So either stay the same or lose. So, and therefore, this game is not sufficiently fair to be called a martingale. So this, in my books, is not fair, as it is not fair from day to day. Okay, but what would be a natural way to construct a fair game? Well, I can still base my game on a sequence of independent coin tosses. So this will be EI. So independent. Such that the probability of EI is 1 is the same that the probability of E1 being -1 and is 1/2. And then what I can do, I can simply say I win or lose according to what the coin shows me. So it would be the sum from 1 to n of I, right? So if on day n, so this is like a random walk. And if I know I'm somewhere at day n with my random walk with some amount of capital, then what happens before the next day, I will either lose £1 or win £1. So on average, I will stay with the same amount of money. But so this game is maybe too simplistic. So what we want to put some bets every day, right? So so every day I want to be able to bet some amount of money, which can even be random. So I don't need to tell you in advance what the sequence of bets is on each day. But what is extremely important, so maybe let me put it here. So this is our bet on day I. So what we don't want to happen, we don't want this bet to depend on the future. So it may depend, so it may depend on the past, so on what happened before that day when I'm playing, right? So if, for example, I won quite a lot by the day n, then maybe I can increase my bet just because I have a lot of money by now and I can take the risk. But it can't depend on the future of my random game. Okay, so this still feels like a fair game if I do that. And let's see what I have achieved. So if I compute, so I want to formalize this concept of fairness, and the formalization will be this. If I compute the conditional expectation with of xn with respect to all the information which I have by day n, not including the day n, so by day n-1, which is the outcomes of the first n-1 coin tosses, then, so this is the definition of my xn. In particular, if I want to compute this expectation, I can say it is xn-1 plus the last term, which is yn en, right? Now, xn minus 1, it only uses y up to the index n minus 1 and e up to the index n minus 1. So xn minus 1 is measurable with respect to the sigma algebra. So we know what xn minus 1 is, right? So since it is measurable, it is just xn minus 1. And how do we compute the conditional expectation of this? By assumption, our bet should be measurable with respect to this sigma algebra, so we can take it out. And En is independent from of that sigma algebra, so we simply take the expectation of En, which is 0, right? And this gives us xn minus 1. So my conditional expectation of what I will have on day n, given the information which I have by that time, should coincide with what I have by that time. So this is what it means to be fair. And in general, when we talk about the filtration, you can interpret it as the information which you have by day n. So if I go back to the definition, for example, so fn here, so f0 is the information which I have on day 0, f1 is what I know by day 1, and so on. And you can see it even better if you look at the natural filtration, because so this sigma algebra contains all the information about the first 3 random variables. You can assume you know those values. And the nth sigma algebra will contain all the information about the first n random variables. So the longer you observe your process, if we are talking about the natural filtration, the more information you get about your random process. So this is how we can think about the filtration. Okay, so this explains what kind of processes I want to be martingales. And now we can give the definition, which is not going to be this one. But this is what the original meaning of the word martingale is. It is this piece of harness which apparently is used to keep the horse's head from going up too much. And we see that we will have exactly the same constraint or similar constraint for a martingale. So we will request that it doesn't deviate up and it doesn't deviate down, because we want our game to be fair. So on average, it should go like this. So if it goes up on average, then it is a favorable game, so not fair. If it goes down, it's not a favorable game. So this is why this term was used to talk about the martingales. But now, finally, our definition of a martingale. So a random process, xn, so let me emphasize that n starts with 0, so is a martingale. With respect to a filtration, okay, so I will want to add something else here, so let me write it here, is a martingale with respect to a filtration Fn if the following 3 properties are satisfied. So first of all, I want xn to be adapted to Fn. So xn is adapted to Fn. Secondly, I want each xn to be integrable. So the expectation of mod xn is finite for all n. Now, I don't request them to be uniformly bounded. They can grow, like the expectation of xn, of mod xn can be equal to n, and will grow to infinity. That's fine by me. I just want each of them to exist. And the most important property is property 3, which says that the conditional expectation of xn, given the past, given the information on the previous day, fn minus 1, must be the same as xn minus 1 for all n in n. So this is the definition of a martingale which was suggested by the by our wish to have a fair game. Now, we will sometimes talk about sub-martingales and super-martingales. For the definitions of them is very, very similar. So sub-martingale, or let me use a different color, super-martingale. So sub-martingales will be favorable games. It will be when our expected winning on day n, given the past, is greater or equal than what we had on the previous day. So this is sub-martingale. We have to replace the equality by this inequality here. And super-martingales are unfavorable games, games where on average we lose. And as you have guessed, I'm sure, those are defined by changing the inequality to less or equal. Now, clearly, if a process is a sub-martingale and we change its sign, so if our original process xn was a sub-martingale and we consider minus xn, then minus xn will be a super-martingale. So they are connected in this very simple way, and therefore there is no need to study both of them. So if we understand sub-martingales, it means we understand super-martingales. So in this course, we will try to understand martingales and sub-martingales, and we will not be talking about super-martingales for this very simple reason that that all the information about them follows from that for sub-martingales. Okay, so a few very simple remarks. First one is that this property of fairness, which is stated here between adjacent days, is actually true between any days. So if I take any n greater than m and look at the expectation of xn given fm, then what I will get is xm. How I can see that? I can see that by using the tower property. So that was one of the many properties we have proved and never used. So tower property, which says that if I want to condition on a very small sigma algebra, which is fm in this case here, then I can first condition on a bigger sigma algebra and then condition on that smaller sigma algebra, and this two-step process will give me the same result. So what I will do, I will first condition xn on fn minus 1, which is bigger than fm, and then condition on fm. But then from property 3, I know what this conditional expectation is. I know that it is xn minus 1. So you see, I've managed to make one step. So now, instead of conditioning xn on fm, I'm conditioning xn minus 1 on fm. So I can just proceed by induction, and the next step will be xn minus 2 fm, and so on. So I wait until I reach x. Maybe let me do this. So I wait until I reach xm plus 1 conditioned on fm, and by property 3, this is just xm. So my process, if it is a martingale, is fair between any 2 days. And clearly, the same is true for sub-martingales. So if I had this inequality here, then I would be having greater or equal here and greater or equal at the last step. So I would be able to say that the process is also favorable between days n and m. So that's the first comment. And the second comment is that the expectation of a martingale never changes. So the expectation of xn is the same as the expectation of xn minus 1, xn minus 2, and so on, and they all are the same as the expectation of x0. And very often x0 is just a constant, maybe 0, if you say I start with the 0 capital, and then you can just say all the expectations are equal to 0. So why is that? Let's look at this formula with m equals 0. So this proves that the conditional expectation of xn is equal to x0. But one of the properties was that the expectation of the conditional expectation and its original random variable is the same. So we say that the expectation of xn is the same as the expectation of this conditional expectation, and this is the same as the expectation of xm. So the expectation never changes. And also one tiny comment is that, so your definition is of a martingale with respect to filtration, but sometimes in the exercises you will see something like prove that xn is a martingale, and no filtration will be mentioned. This means you're supposed to work with the natural filtration of your process. Okay, so this is the definition. Let's look at some examples. The first one is the one which I mentioned already. So it's when xn is equal to this betting games where those are sigma E1, E n minus 1 measurable. So in particular, the random walk, and since I'm going to mention the random walk quite a lot, I want that we have it somewhere. So this is the definition of the random walk. So x0 in both processes here is equal to 0. If you draw a graph of random walk, then you see that you start at 0, and then you do steps up and down randomly. So something like that. So this is a random trajectory. So if you interpret it as a betting game, then that one, so here you have been quite lucky, so you have been winning, but clearly there are plenty of trajectories which go down or go up for a little bit and then go down. So this is what we mean when we talk about the random walk in the future. Second example, here I just want to say that there is nothing sacred about the coin tosses, right? So to have a martingale, you can take, so let's do this. So you can take xn to be the sum of some random variables ui. So I'm changing my coin tosses to something else. And let's see what kind of condition I need to impose on ui to make this process a martingale. So I will just repeat the proof from the first example. So I want to prove that the conditional expectation of xn given the natural filtration, so I will denote the natural filtration by sigma n simply to save us some time. So I want this to be xn minus 1. So as before, this is equal to xn minus 1 plus un. So xn minus 1 is measurable with respect to sigma n minus 1. And then it would be convenient to know that un is independent, right? Because if u is n are independent, then I can simply say that this is the expectation of un. And then if I want to say that the answer is xn minus 1, I want this to be equal to 0. So this means I can create a martingale by taking those sums where UI are just independent with mean 0. They don't even need to have identical distribution. So it's like a random walk, but where your steps have much more flexibility. You can go up and down by any amount which is supported by the distribution of your random variables. So this process is a martingale. Now, third example is something we have seen already, the Galton-Watson tree. So let me remind you what the definition was. So we fix an offspring distribution, which gives us the probabilities of having any integer number of children from 0 to plus infinity. And we assume that it has a finite mean, we denote it by A. And by Zn, we denote the size of the generation, of the nth generation of this tree. So here, each individual has a random number of children corresponding to this offspring distribution and independently of all other individuals. So we have already seen that the conditional expectation of Zn with respect to the sigma algebra generated by Zn minus 1 is A times Zn minus 1. Now, I need to fiddle a little bit with this sigma algebra because sigma Z1, sigma Z2, sigma Z3, and so on, they are not growing sigma algebras. So if I know the value of Z10, I don't, so like here, if I know the value of Z2, I do not necessarily know the value of Z1, right? Because those 6 values, if I cover this part of the graph, they could have been produced in many different ways. So if I want to be talking about the martingales, I need to be looking probably at the natural filtration of my process. So I want sigma Z1, Zn minus 1. But now, since this sigma algebra is bigger with respect to this one, it's easier to be measurable with respect to this sigma algebra. So if I know the answer here, I will have the same answer here. So here the answer is A, Zn minus 1. So this means Zn is a martingale with respect to the natural filtration, which I'm going to omit, if A equals 1, right? Also, what we can do, we can look at the process Zn. So if we see that Zn is growing by a factor A every time, then we think probably the right scale for this process is A to the power n. So what we can try to do is to rescale it by A to the power n, if A is different from 1, otherwise nothing happens here. And we will see that this process is always a martingale, not with any value of A, is a martingale. Very easy to see that, Zn A to the power n, given sigma n minus 1. So sigma n minus 1 will be the short notation for the natural filtration sigma here. So we know what the conditional expectation of Zn is. It's A Zn minus 1. So we end up with Zn minus 1 over A to the power n minus 1. So this properly rescaled process is always a martingale. So maybe to avoid confusion, let me say for all A. The last example in this video is that of the Poya urn. So we remember how it works. We start with just 2 balls, green and red, at time 0 in the urn. Then we pick one of them randomly, and we put it back together with another ball of the same color. So here with probability 50-50, we add a red ball. Now at step 2, we again pick one of the balls from the urn, but now we are more likely to pick a red ball, and we replace it together with another ball of the same color. So here, now our probability to get a red ball is even higher, but it's still possible to get a green ball. So maybe at this step we get a green ball, and then we need to put another green ball into the urn. And we decided to look at the process, which is the proportion of red balls in the urn. And then I asked you to compute the conditional expectation of Mn given the past. So I think I denoted this by the number of added red ball at step 1 up to the number of added red balls at step n, but basically it's all the past up to the time n-1. I asked you to compute that. I told you I will tell you the answer later and show why this is true. Well, the answer is actually mn-1. I hope you had a chance to have done this calculation, because it is an interesting example. I think when you look at it, you should be surprised, because what I told you that our process is fair, right? And it's not clear how this Poyer urn is fair, because if it has more red balls, then clearly we are even more likely to put another red ball in here. So doesn't it contradict the intuition of a martingale a little bit? So think about it, and we will discuss it in the live class.